Assalamualaikum warahmatullahi wabarakatuh. We are from Group 12, and in this video we will be presenting on the topic the predator-prey model, also known as the Lotka-Volterra equations. Let's begin with the introduction. In nature, the population of living organisms are constantly changing. One of the most fascinating examples of this interaction between predator and prey, and their prey, like foxes and rabbits. To study the predicts these changes, we use mathematical models. The Lotka-Volterra model is a well-known system of two differential equations that describe how predator and prey population affect each other over time. What makes this topic interesting is that we can use eigenvalues and eigenvectors to analyze the stability of the system. This helps us understand whether the population will remain stable, rise and fall in cycle, or eventually die out. This model has real application in biology, ecology, and conservation science, and it shows how mathematics can help us understand complex natural systems.
Developed by Alfred Lotka and Vito Volterra, this equation is a pair of first-order, nonlinear differential equations used to describe dynamics of interacting populations between prey and predator. It is dx over dt equals to alpha x minus beta xy, and the other one is dy over dt equals to delta xy minus gamma y. As the definition, alpha is the prey reproduction rate, beta is the rate of predation, gamma is the predator natural death rate, delta is the predator rate of growth due to predation, while x is the number of prey and y is the number of predator. Also, alpha s is equal to exponential growth of prey, while negative beta xy is the loss of prey due to predation. Delta Sy is the growth of predator population due to consuming prey, and minus negative gamma y is the exponential decay of predators when there is no food, or in other words, prey is available.
Now, let's look at the assumption behind the model. First, prey have unlimited food and habitat, so without predators, they grow quickly. 2. Predators only eat the prey, so without prey, they die off. 3. Predators have an unlimited appetite, so that they never stop hunting. 4. Every predator-prey interaction means loss for prey and gain for predators. 5. The environment stays the same, no evolution or favoritism for either species. So, if we look here, there are several formulas that can be represented for the prey population and predator population. The first one, dx over dt is equal to x over alpha xy, that represent for the prey population or x. The second one, dy over dt is equal to beta xy minus y, that is represented for predator population y. Now, related to the previous slide, we know that we're going to let x is equal to the number of prey, y is equal to denotes the number of predators, dx over dt is equal to instantaneous growth rate of the prey population, dy over dt is equal to the instantaneous growth rates of the predator population, t is equal to times, and alpha and beta is equal to positive real parameters that describe the interaction of the two species. Now, let's continue with the equilibrium solution. If we look at the first equilibrium solution, we're going to see that it's equal to 0, 0. So, the Jacobian becomes 1, 0, 0, negative 1. In order that, eigenvalues are lambda 1 is equal to 1 and lambda 2 is equal to negative 1. If we look at here, we see that one is positive while the other one is negative. So we can see that it is unstable. This point is called a saddle point. Now we're going to move on to the second equilibrium, which means that the first is 1 over beta and the second one is 1 over alpha. So that the Jacobian becomes 0 negative alpha, beta 0. So the eigenvalues are lambda 1 is equal to I and the lambda 2 is equal to negative I. I is represented as the imaginary numbers. This means that the populations don't go wild or vanish. Instead, they oscillate or will go in loops over time. They move in closed elliptical path like a repeating cycle of infection and recovery. This is stable, but not stable in the everything settle down forever way, which means that it is not asymptotically stable.
Here are the graph results. Figure 1 illustrates change in the predator and prey population against time, and two sinusoidal curves out of phase are observed. Next, figure 2 is a phase plot of predator population against prey population to compare how the numbers change relative to each other. It is observed that the population oscillate on a closed ellipse around the fixed point. In the last graph, figure 3 is a more general phase plot that demonstrates the effects of varying initial population size of both species. In this study, we used the Lotka-Volterra model originally designed for predator-prey system to simulate the spread of COVID-19. In this case, infected individuals act as predators and susceptible individuals as prey. We found two key outcomes. First, an extinction point where both populations drop to zero. This is mathematically valid but unrealistic in real life. Second, a stable cycle where the population rise and fall in a repeating wave. This is more realistic and match the way COVID-19 cases tend to surge and decline over time. Our MATLAB simulation support this, showing sinusoidal wave in population size and phase plot with closed loop, meaning the system goes through a repeated cycle. However, the model has limitation. It assumes no immunity, no outside influence, and constant environment. That doesn't reflect reality, where factors like vaccination, mutation, and human behavior play a big role in how COVID-19 spreads. In conclusion, while the local Volterra model simplifies things, it offers a useful way to understand how infectious disease can behave over time. It shows us the rhythm of infection spread, but to make accurate prediction, we would need more complex model with realistic factor built in. In conclusion, our project explored the Lotka-Volterra predator-prey model and how it helps describe changes in population dynamics. By solving the system using differential equation and analyzing it with eigenvalues and eigenvectors, we were able to determine the behavior near the equilibrium points when the population stay constant, fluctuate, or collapse. This application shows how powerful mathematics is in solving real-life problems, especially in understanding ecosystem and supporting environmental decision-making. Through this, we've seen how math is not just about numbers. It's a tool that connects us to the world around us.